In this lesson, we will look at the velocity kinematics of a robot manipulator. By this problem, we already said that knowing the velocity of the end effector, velocity vector of the end effector, given the velocities of the various joints, that is the problem of velocity kinematics. We will approach this through a simple two-link planar manipulator example. What's a tool planar manipulator? With it has got two rotary joints, and these are the two links, and they are in the plane of the paper, and they're moving the same plane, and they move about the third z-axis, which is perpendicular to the paper, plane of the paper. Well, given that, suppose let L1 be the L1 and L2 be the link lengths, and we are interested in finding out, trying to relate the angular velocity of this joint and angular velocity of this joint to what kind of effect it will have on the end point velocity. And this is a end point velocity would have two components, only x and y being a plane. So we'll first try to find what the expression for x and y, and then find the velocities. What are the functions of x is equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2 is the angle between L1 and L2. So therefore, along the x-axis, the component will be L2 cos theta 1 plus theta 2. So x is L1 C1 plus cos theta 1, I write it as C1, and cos theta 1 plus theta 1 plus theta 2 as this cos C12 for brevity of writing. So L1 x is L1 C1 plus L2 C12. Similarly, y is L1 S1 plus L2 S12, this component. So, but you see that both are functions, x and y are functions of theta 1 and theta 2. Therefore, the small changes in x and y are given by dx is equal to dou x by dou theta 1 into d theta 1 plus dou x by dou theta 2 into d theta 2. Given the expressions for x and y, you get minus L1 S1 minus L2 S12 d theta 1 minus L2, that is the partial differentiation of the second term, L2 S12 d theta 2. Similarly, change in y, infinitesimal change in y will be L1 C1, differentiation of this partial differentiation, L1 S1, L1 C1 plus L2 C12 times d theta 1, L2 C12 d theta 2. And now you see that dx and dy both are related to d theta 1 and d theta 2 through this matrix. And this matrix is called the Jacobian. What is it doing? It is relating the joint velocities. You multiply the joint velocities, infinitesimal changes. With this matrix, you will get the end changes in the end point velocity in terms of x and y. Or if you divide this by the time, well, you can call it a dp to represent as a single term. If you differentiate this by, or rather divide by time, you will get the velocities. And here, of course, your d theta 1, d theta 2 will become d theta 1 by dt, etc., which will be theta 1 dot and theta 2 dot. So you will get x dot y dot equal to j times theta 1 dot theta 2 dot. Or your v will be equivalent to j theta dot. This j, is this, and we can write it as j1 and j2 as the two columns. V is equal to j1 j2 theta 1 dot theta 2 dot. Or you can write it as V is equal to j1 theta 1 dot plus j2 theta 2 dot. Okay, this velocity relationship of the endpoint velocity v with the joint velocity vector theta dot is determined by J, the manipulator Jacobian. Well, we have seen that v is equal to j1 theta 1 dot j2 theta 2 plus j2 theta 2 dot. That means suppose theta 2 dot is equal to 0. There is no joint velocity at the second joint. and the joint velocity theta 1 dot is equal to unity, then V will be equivalent to J1. Similarly, when theta 1 dot equal to 0 and this is unity, velocity will be only equal to the second column. Therefore, as you can see, the first column is influenced only by the first joint, second column by the second joint, and so on. There will be as many columns as the degrees of freedom. Okay. And then for the tooling planar manipulator that we have taken up, the Jacobian is going to be this, and as you can see this Jacobian, as you keep as theta 1 and theta 2 change, you will find that the Jacobian changes. So Jacobian is not constant for to give a relation between the endpoint joint velocities and the endpoint velocity. It depends upon the particular configuration. At that position, what are the various joint variables that will decide the Jacobian. You need to keep that in mind. So that is what makes the velocity kinematics a little more computationally more intensive. Okay, now we'll try to extend this for a n-link planar manipulator. We'll try to derive an expression for an n-link planar manipulator. Before that, suppose this is a typical n-link planar manipulator, and we are interested in finding out the endpoint velocity. The endpoint velocity, this is not a planar manipulator, so it will keep rotating. The frame attached will be rotating, and it will have velocity along x, y, z. Not only that, even the frame will have 3 velocity components along x, y, about x, y, and z on the frame. So in all, it will be 6 degrees of freedom, and there will be 6 component velocity vector. So what we will do is similarly uh, the the j vector, the j column is going to be a 6 column vector. Of that, the top 3 will use for linear velocity component, they'll contribute to the linear velocity component, and the bottom 3, let us say, will contribute to the angular velocity component. Well, taking it that way now look at a general end degree of freedom manipulator. We will see, we'll take one joint and see if it is a rotary joint, how it will affect the endpoint linear velocity and angular velocity. Well, suppose theta I dot is the velocity. This is a rotary joint. Suppose this is a rotary joint, and the velocity, angular velocity at this point is theta I dot. Then the linear component JLI dot QI dot. JLI times QI dot will be omega R, omega cross R vectorially. Okay, that is the linear velocity at this point due to an angular velocity at this joint, omega cross R, and that R happens to be this vector. It is nothing but the this vector minus this vector. Okay, so that is O end minus OI, whatever, OI minus 1. Okay, all right. So this is going to be that vector Ri minus 1 is that multiplied by whatever is that angular velocity, that is going to give you the linear velocity component at this point due to this joint motion. Okay, and that omega I will be along this vector, about this vector, so we call it about Zi minus 1, we call it Zi minus 1 cross Ri minus 1 is Zi minus 1 times the theta I dot, that is omega I. I'll take out theta I dot. This is how we write this. Okay, what about the angular velocity contribution? Well, as it rotates like this, this frame, you take this as a fixed, all these are rigidly connected, they're not moving. These joints are not moving. So if it is moving, the whole thing will move as a rigid thing, and the angular velocity of the frame attached to the end effector will be the same as the angular velocity of this vector about Zi minus 1. So Zai, the bottom part of that column, Jai times Qi dot is going to be just omega I, that is going to be equivalent to Zi minus 1 times theta I dot. Okay, so The two components that you will have if it is a rotary joint are these two. I can write Zi minus 1 cross Ri minus 1 comma E and Zi minus 1. This will be your column, ith column of the Jacobian if it is a rotary joint. Suppose it's a prismatic joint. Well, if it is a prismatic joint, the linear velocity, if it is, suppose it's moving like this, the endpoint also, if it is a rigid frame, the endpoint also will move along like this only. So it will be the same as this velocity, which is nothing but d z I minus 1. Z I minus, rather, d dot. D is the change in displacement and d dot is the velocity. So in this direction, Z I minus 1 vector direction. So Z I minus 1 di dot, that is the linear velocity. And what is the angular velocity? Because there is no rotation here, this doesn't rotate either. It is simply moving parallel. The frame is moving parallel like this. So that is 0. So for a prismatic joint, it will be just Zi minus 1. The column will be Zi minus 1 and 0. This will be top 3. Bottom 0 is 0, 0, 0. Okay, so this is, that means, as I said, this Ri minus 1 comma E is OE minus OI minus 1. And Z are determined from third. And so what is Z? Z happens to be the for the rotation matrix, the third column of the rotation matrix. And so you can obtain both from the third and fourth columns of the H matrices, H40, H60, H6I, for example. That will give the third and fourth columns will give Zi and the Z, I'm sorry, Z, Hi minus 1 comma 0 will give you the fourth column of that will give you the displacement, this distance, XYZ components of this distance. From you subtract that from H60, which will give you the three components of this with respect to base frame. If you subtract vectorially, you'll find that you'll get Ri minus 1 comma E. Therefore, basically, you need the H matrix, various H matrices that we derive from our link parameter table, and then you calculate the homogeneous transformation matrix for each row you calculate, and then you develop the various homogeneous transformation matrices H60, H10, H20, H30, and so on. And then you'll be able to get the third and fourth columns of these matrices will help you develop this geometrics. So, okay, we'll take an example. For example, what you are interested is the endpoint velocity of, in the case of a RRP manipulator. It is RRP, you get Z0 cross O3 minus O0, Z0, Z1 cross O3 minus O1, Z1. Mind you, column number is I minus 1 is Zi minus 1 is what you get here. OE minus OI minus 1 will be O3 minus O0 and so on. Next one is Z1 and next is Z2 because this is prismatic joint. So, for a prismatic joint, this is the type and you get Z2 comma 0. Of this, O0 happens to be, by our choice, we'll make it as the reference coordinate and frame, and that will be O0 will be 0, 0, 0, and Z0 is a vertical line, and we can make it as 0 along the unit K direction, and it will be 0, 0, 1 for the vertical axis. We start with that, and other things we obtain from fourth column of H10, H20, and H30. You get the O1, O2, O3. Z1 and Z2 are obtained from the third column of H10, H20. So, as I said, they can be calculated using the link parameter tables. Now, at this point, we'll also introduce the topic of inverse velocity kinematics. What is inverse velocity kinematics? You just now saw that V is equal to JQ dot. Okay. Well, if you know, that is, V is jq dot will give you, given the joint variable velocity, you can obtain the end point velocity vector. Given the end point velocity vector, multiply that by the Jacobian inverse, J inverse, you will get the joint variable, joint velocities, q1 dot, theta 1 dot, theta 2 dot, d3, etc. Okay, and for a tooling planar case, if you take J will be this, and J inverse, you multiply with the end point velocity. Suppose that is Vx and Vy are the two components of the tooling planar manipulator end point velocity. You multiply that with this. Then for theta 1 dot, you get this expression, theta 2 dot, you get this expression. And you will find that S2, when S2 is equal to 0, which may be the case, that is sine theta 2, which will be the case when theta is equal to 0 or pi, then you'll end up with infinity. And so that's the case of a singularity. Actually, that is a case of fully retracted or fully extended arm. You can't, then degree of freedom is reduced to 1 from 2 in those cases. So that is what mathematically this demonstrates also. Actually, what happens to your Jacobian when theta 2 is equal to 0 is sine theta 2 is equal to 0 is this. You find the two columns are like this of the Jacobian. Actually, they are linearly dependent, and as such, the degree of freedom is reduced by 1. So, degree of freedom has reduced by 1 at these points. Yeah. Now we'll see a couple of cases, simple cases, and see how we can arrive at the Jacobian. Jacobian, as we have seen discussed earlier, can be complicated, written like this, because you need to derive the link parameter table and then the homogeneous transformation matrices, and then get your required H matrices to get this kind of data. All that exercise will be definitely required when you exceed beyond the 3 degrees of freedom. Once you have 4, 5, 6, typically, naturally that will be very much required. Computationally go through this, and of course that will be done by a computer. And for a simple case, you can also see how to write a Jacobian. For example, I take a RRP manipulator we discussed earlier. For RRP, suppose you fix the frames like this, and at one point, it has rotated by an angle theta 1, and this also moved by an angle theta 2, and the current joint variable linear motion has taken it to the between these 2 points, end point, and this frame has gone to D3, let us say. And if you look at this, and well, what I'm interested is developing this. In this, what is Z0? Z0, we know 0, 0, 1. And Z1 is along this direction, which is actually 90 degrees to this Z2 line. And it is once we originally, when without rotation, it is in line with Y0. After rotation by an angle theta, it makes a positive angle theta 1 with about from 2 Y0. Therefore, you can see that it makes an angle 90 plus theta with x0. Therefore, your z1 components along x0 is minus s1, along y0 is make an angle theta c1 cos theta 1, and along z0, of course, it has no component, so that will be just 0. Similarly, z2 is this, and you can see its projection on this plane. Taking this angle as theta, making an angle from the vertical, whatever it makes. Originally, it is in the vertical position. Once it turns by an angle theta, it's like this, and its component is sine theta 2 on the horizontal plane. It will be sine theta 2. That component multiplied by this component along x0 is cos theta 1, along y is sine theta 1. So C1 S2, S1 C2, and along the vertical it has got a component cos theta 2. So you readily got the three z directions, 3 by 1 vectors for z0, z1, z2 that you will be needing here. All you will need are r0e and r1 to end. R1 to end is only, suppose this is the distance after this joint variable d3 has moved, by some distance, d3 into along the z2 vector. So d3 z2, and from OE to O0 will be this plus this vector, which is L0, whatever is this length. This is constant, physical constant. L0 times Z0 plus D3 times Z2. So R0 is that. So L0 is a constant known to you. D3 is a joint variable known at that instant of time. So you know this also. All you need to do is substitute that and do the cross multiplication of the vectors. Then you will end up with this matrix, which is 6 by 3 matrix for the 3 joints. This is the, well, once you have this, you can always multiply by your joint velocity theta 1 dot, theta 2 dot, and d3 dot, and obtain the 6 by 1 vector for the end point velocity. We'll look at one more example. This example is reasonably simple. Again, this is SCARA manipulator. It has got all this rotation axis, vertical. These two are upwards, these two are downwards. This is rotary, prismatic, and rotary again. Okay. So in this Z0, Z1 or 001, Z2, Z3, or Z2 and Z3 required are 0, minus 1 because they're downwards. And again, when you look from top, like your two-link planar manipulator, it is like this. So it is, this theta 1 has moved by some distance, theta 2 moves by some more distance. When you look from top, this is the top view for the two links. This point, of course, is at this point. And then you find that we'll fix the first frame here. So, and O1 with respect to that will be A1C1, A1S1, and 0. And this point O2 will be this plus this A1C1 plus A2C12. Okay, like this. Similarly, A1S1, A2S12, and the Z component will be 0 at this point. Only difference for O4, only difference is it is down along Z axis by a distance d3, d4, minus d3, d4. Otherwise, x and y components are the same as O2. So I have these two are the same. Now you got all the data necessary. Once you have that, just multiply, do the necessary cross multiplications. Well, you got already 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, minus 1 for Z4. Yeah. Once you have that, you do the cross multiplication, you have the J matrix available. As I said, for simple cases like this, it is possible to develop the Jacobian, but when you have 4, 5, 6 degrees of freedom and 6 joints, you will find that you need to take to recourse to some more better programming approaches to this and arrive at the Jacobian. Many times, of course, you have to see that Jacobian is invertible or not, because when you want to use it for inverse velocity kinematics, which is the more important function, because the end, you would like to develop a certain trajectory. The trajectory is known to you. You would like to know what are the joint velocities set at that point, that instant, to be able to produce that end effector velocity. So for that, you will be needing to develop J, and then developing the inverse, and then multiply with the end point velocity vector to get the joint variable velocities. Well, this will serve as a brief introduction to the velocity kinematics of robot manipulators.